So today we are going to be looking at sorting. Sorting is actually one operation that computers love to spend their time on, so it's estimated that 90% of the time spent by all computers is on sorting numbers, right. So it's really a problem which requires attention, requires consideration, and so we need to develop good algorithms for it. So in the last class, as I had said before, you have looked at heap sort. So today we are going to look at another sorting algorithm. So where does sorting occur? Most oftenly in databases, right. When you are searching in databases, you want to keep the data sorted in a certain manner so that the search becomes efficient, right. Recall that search is more efficient, when you have the data sorted. There are a lot of settings in computational geometry, computer graphics, where sorting is essential, right. So I am not going to go into more of these applications, but we are going to look at certain sorting algorithms. So sorting algorithms also give us an idea of different algorithm design techniques. So actually this is a point we have not spent any time on yet. So algorithm is, what is an algorithm? It is a way of solving a problem, and there are certain techniques that people adopt to design algorithms. Given a particular problem, how do you design an algorithm for it? So there are a certain standard set of techniques, and sorting shows you some of those techniques. So today we are going to look at one such algorithm design technique through a sorting algorithm. Yeah, there is also what is a lower bound on sorting, right. So what this means is that no sorting algorithm which requires comparisons, no sorting algorithm can sort n numbers in less than n log n comparisons. There cannot exist any sorting algorithm. Okay. Right. So we are also not going to be spending time on this, but this fact is useful to prove lower bounds. So this is called a lower bound on a certain problem, right. This fact is used to prove lower bounds for other problems as well. So this was as far as the motivation for why sorting, why are we spending so much time on sorting is concerned. So far we have seen insertion sort and selection sort. These are two sorting algorithms with the worst case running time of n squared. Yeah, and there are two algorithms I should also have written: quick sort. Actually heap sort has a worst case running time of n log n, and one algorithm that is missing from this list is quick sort, which has a worst case running time of n square, but a average case running time of n log n. Yeah. So today we are going to see another algorithm, and the paradigm, the algorithm design paradigm that is used here is what is called divide and conquer. So some of you might have seen divide and conquer in your earlier CS course. Basically what the idea is that given a certain problem, to solve the problem you first divide the problem up into parts, yeah, two or more parts. Then you recursively solve those sub problems, so recursively solve the problems on those parts, right. So that is what is called the conquer step. So recursively solve the problems on those parts. When I say recursively solve, how do you solve the problems on those parts? By once again dividing them into smaller parts and solving the problems on those smaller parts, and so on and on. So use the same algorithm to solve the problem on the smaller pieces, and once you have the solutions for the smaller pieces, you need to somehow combine the result to get the solution for the original problem. So that is what is called the combine step, and we will see this through an algorithm for the sorting problem. We are going to look at what is called the merge sort algorithm, right. Some of you again must have seen this before. If you have seen it, it is okay, because we will see at least a different way of analyzing the algorithm. So what is sorting? Basically you are given n numbers which you need to put in increasing order, let us say, okay, and let us say S is the set of n numbers. What we do is we would split n into two sets, S1 and S2, two sequences S1 and S2. So this is the divide step, and the split would be such that S1 and S2 would contain roughly half of the elements of S. Okay. Now recall this should look very similar to you to another algorithm, the quick sort algorithm, right. There also we did a division at the very first step, right. But how was the division done there? It was not equal, right. So in the divide step there we were dividing the problem into two sub problems but those two subproblems were not equal in size. One could be smaller than the other, right. But here we would make sure that we divide it into two equal subproblems. Equal by mean the number of elements in the two subproblems are equal. So, if S1 contains the first, let us say n by 2 elements, n by 2 ceiling, then S2 contains n by 2 floor elements. What do I mean by first n by 2 elements? Not the first n by 2 in a sorted order, because I do not know what the sorted order is. S is just some arbitrary collection, some list, some sequence. I just take the first n by 2, call that S1, the next n by 2, call that S2. Right. Now, conquer step is that I would sort these two sequences. I would sort S1, I would sort S2. Yeah. So, recursively I am solving the same problem. And then once S1 and S2 are already sorted, I have to combine. I wanted a sorted sequence for S. I have S1 as one sorted sequence, I have S2 as another sorted sequence. But what is S? S is not, so if I say what is the sorted sequence corresponding to S, it is not just S1 followed by S2, no guarantee that that is sorted, right. So, I need to what is called merge S1 and S2 into one sorted sequence. That is called the merge step or the combine step here. Okay. Now, who can tell me? So, in the case of quick sort, the divide step was I take an element and I compare, that is the pivot element, and I compare every element against this element. Yeah. We had this procedure called partition which was helping us do that, right. That was a more involved procedure because we were trying to do it in place, right. So, we were kind of just swapping elements till we got two sequences, right, one containing all elements less than the pivot and another containing all elements greater than or equal to the pivot, right. That was the division step. How much time did we spend in division there? Order n, because we had to compare every element against the pivot. How much time do we spend in the division step here? Constant time, right, because we are just saying if it is an array, we just say okay, this is S1, this is S2, we are not copying anything from anywhere to anywhere. That is one difference, right. We will come back to the conquer thing. Let us look at combine. In the case of quick sort, we are doing the same thing, right. We partitioned, then we said okay, we will quick sort one part, we will quick sort the other part, right, and then we will combine. Did we have to do combine there? No, because we could just take the first sorted sequence, put the pivot element and then take the second sorted sequence, and that would be the sorted sequence for the entire thing, right. So, how much time was combining there taking? Constant time. Here combining will not take constant time. Here we have two sequences and we have to combine them. We will see that it will take order n time, right. This is also called the merge step, and the name merge sort is deriving from this step, right. So, everyone understands what the algorithm is. So, for instance, this could be this is a pseudo code for the algorithm. I give you an array A, P and R identify the part of the array, the lower and the upper bound, which needs to be sorted, which needs to be merge sorted, right. So, if P is less than R, only then we need to do something. P is the lower and R is the upper index. So, Q is the midpoint, P plus R by 2. Yeah. So, I am going to, so this is the division step, these two are the recursive solving, the conquer steps. I am saying from P to Q sort the first part of the array, from Q plus 1 to R sort the second half of the array, sort using the same merge sort procedure, right. And once you have this part and this part sorted, you have to combine. For that I have another procedure called merge, right, to which I specify P, Q and R, right. So, this procedure merge, the definition is the following. Okay, this is what it is doing, but what is the definition of merge? It is going to take the two sequences, one sequence is from P to Q, the other is from Q plus 1 to R, and merge them and make one sorted sequence which will sit in P through R. Yeah, that is merge. And how does merge proceed? That is essentially what the merge algorithm is doing, and we are going to see examples of it. So, do not worry, but let us just read through this and you will understand a little bit of what merge is going to do. It is going to take the smallest of the two topmost elements of these two sequences. So, what do I mean the smallest of the two topmost elements? What is the topmost element of this sequence? The first element, topmost of the first element, which is P, or the element at location P, A of P, and the topmost element of this sequence is A of Q plus 1. I am going to take the smaller of these two, right, and put it into the resulting sequence. Whichever is the smaller, right, when I have to merge. So, if I have to merge these two sequences, which will be the smallest element of these two sequences? It will be the smallest of this and these two, the smallest of these two numbers. I do not have to worry about any other numbers, because this is already sorted and this is already sorted in increasing order. So, I take the smaller of these two, and that gives me the first element of my resulting sequence, right, and in this manner I can continue building up the resulting sequence, and we will see how that is done. That is done, right. So, that is merge. Now, let us look at an example for merge sort. This is my sequence, right, as you can see it is not sorted, 8 element sequence. So, the first step is a divide step. We will divide this into two parts, right. So, one part is this, okay, and the other part is this. This is the division, right, and I have shown it lower down because I am kind of doing a recursive call of merge sort. So, this corresponds to like one level of recursive call, right. So, first I do a merge sort here, this is another merge sort call, then I will do another merge sort call here, and so on. So, this is a recursive call on this part of the sequence, on these 4 elements, right. And how is this done? This is done by once again dividing this into two parts. 8524 is one part and the other is the other part, and I do a recursive call on this part now first. First I do the division, then I do a recursive call on the first half, then I do a recursive call on the second half, right. तो अभी तक कुछ भी नहीं हुआ है, we just seem to be doing divisions and doing recursive calls, as you can see, right. And how do I sort this part? Once again I divide it into two parts, 85 and 24, and I do a recursive call on 85, just a single element sequence. And what is the solution for this when there is only a single element? That is itself a sorted sequence. So, 85 goes back. So to say we go back to the previous, to the parent calling procedure, right. So, that is 85. So, this is the sorted first half, and this goes down and this is also sorted. So, this is the sorted this, and now we have to do the merge at this call, right. So, we have to merge this sorted sequence, which is just 85 sitting in this blue oval, and the other sequence sitting in this blue oval are the two sorted sequences. We have to merge them, right. So, right now we will just do the merge. So, the resulting, as you can imagine, is one sorted, okay, this is the resulting merge sequence 2485, and this is one sorted sequence. So, now we have finished the merge sort for this call that we had done 8524. So, now this can go back up, right. We have finished that merge sort, yeah, and now we are going ready to do the merge sort on the second half. Everyone follows what I am doing here, right. Let me show you the procedure once again. First we divide, then we merge sort the left half, and then we merge sort the right half, right. And when I am merge sorting the left half, what happens? I once again divide, and then I merge sort the left half, and then I merge sort the right half, and when I am merge sorting the left half, what do? I once again divide, and so on and on, right. So, in some sense, so I divide, as you can see, I divide here, I divide into two, merge, first do a merge sort on this, and nothing is to be done here so far. And then how do I do this? Once again I divide, and then I do merge sort on these two, but first I do it here. Only when I am finished with this merge sort will I come back to this one. And how am I doing a merge sort here? Once again I am dividing, this is the trivial case, so this is easy to do, this is the trivial case, so this is easy to do, and I get this sorted sequence, right. So, I have finished the merge sort for this part now, so this goes back. Now, I have to do the merge sort for this part. So, once again I am doing a recursive call on this, I do a call, divide, trivial, merge, 4563, yeah, and now this is my sorted sequence. So, I am now ready to go up, and this is now the two sorted sequences that I get, and now I can merge this. So, I will show you the merge step again more clearly, but you can see which should be the first element, it should be 24, right. So, this is what I will get, the the merge sequence. And now I have done with this part. So, this merge sort call has finished. The merge sort call that I made on these 4 elements, that has finished. So, it goes back up, right. And now I will do a merge sort call on this, right. So, I do one merge sort call here. So, I am not showing you the entire thing, I am just showing you that this entire thing would happen in exactly the same way. 17, 31, 96, 50 would sort, and you will get 17, 31, 50, 96. This goes back up, and then we will merge these two, right. And this is the resulting sequence you will get. So, these are 2 sorted sequences, we can merge them. I will show you how to merge them very quickly, and that will give us the resulting sequence. So, who can tell me how many merge sort calls have I made in all? Log n, 2 log n. How can you count the number of merge sort calls you have made? In this example, how many merge sort calls have I made? N minus 1 actually, order n, right. Why? Because each of these blocks corresponds to one merge sort call. पहले हमने इसके ऊपर merge sort call किया तो इसने 2 में divide किया, एक यहाँ पे और एक यहाँ पे आया. इसको हमने merge sort किया, इस पे merge sort call किया तो वो 2 में divide हुआ, एक यहाँ आया एक यहाँ. इस पे call किया वो 2 में divide हुआ, एक यहाँ यहाँ. इस पे call किया तो कुछ नहीं हुआ, वो वापस number उसी तरह से return होंगे. So, the number of merge sort calls is just the number of nodes in this tree. And how many nodes are there in this tree? Well, you can see that this is the tree. How many leaves are there in this tree? N leaves, right. There are n leaves, so at this level there will be n by 2 elements, at the next level there will be n by 4, n by 8 and so on and on. Sum of this sequence n by 2, n by 4, n by 8, n by 16 so on is n minus 1. You can check that. Yeah, there are many other ways of thinking of it. You can think of it as a complete binary tree on n leaves, and you can apply those formulas that you learnt. Okay? So, this will do exactly n minus 1 recursive calls, yeah, to merge sort. So, everyone follows what is happening? Great. So, let us see the part that we missed out on. How do we merge 2 sequences, right? 2 sorted sequences, I should really say 2 sorted sequences. So, let us say these are 2 sorted sequences. I have S1, S2, 24, 45, 63, 85, 17, 31, 50, 96, right. So, these are I believe coming from 24, 45, 64, 85, are they the same? No, they are not the same, slightly different. Okay. So, these are the 2 sorted sequences, we have to merge them, right. So, what should be clear is that the first element of the resulting sorted sequence is the smaller of these 2, right. So, it is clear that the resulting sorted sequence, which is S, has as its first element 17, right, and then I can strike away 17 from here, because I have kind of removed it and I have put it here. And so, now I have to just merge these 2 sequences, yeah, I have to merge these 2 sequences and append them to this sequence that I am constructing, yeah. So, how do I merge these 2 sequences now? Once again the same idea, which is the smallest element, which is the next element will be the smallest element in these 2 sequences put together, and that will be one of these 2, right. So, the next element should be 24, right, and so I remove 24 out of there and I get 2 smaller sequences like this. Once again I have to find out the smaller of these 6 elements, that has to be the smaller of these 2. So, I will just compare these 2 and I will write that down here. So, I compared, I found 31 is smaller, I write that down here and I remove 31 from this, yeah, and in this manner I can proceed. So, 31, 45 would be the next one to go, these are the things left, then the next one would be 50, we would be left with 63, 85, 96, then the next one would be 63, and then we would be left with 85, 96, next would be 85, left with 96, and eventually we would be taking that and we would have nothing left, right. So, this is what you would get as a result. So, how much time do we take in doing the order n? Why? Is this clear to everyone that we are going to be taking order n time? Right? Because what are we doing? We have these two sorted sequences, we are comparing two elements, the two, right, the two front elements, we are comparing them and taking the smaller of those two and writing them out into one, into the resulting sorted sequence, right. So, with every comparison we are writing out one element. How many elements do we write out in all? As many elements as there are there, right. So, if there are n elements, then I am going to be writing out n elements in all. So, which means how many comparisons am I making? N comparisons, exactly n comparisons actually, right. This was assuming that the two sequences were of length n by 2 and n by 2. Suppose one sequence was of length L and the other sequence was of length m. Right. So, I had one sorted sequence of length L elements and the other sorted sequence with m elements in it, S1, S2. What is the total time taken by merge? L? L plus m, m, L, what should it be? Minimum of, so these are the four choices you have, right, and let us see. Minimum of L comma m, max of L comma m, और क्या? L plus m, कोई और बचता है? None of the above, ठीक है, none of the above. Which do you think is the right one? Min? बताइए मुझे वर्स्ट केस कितना होगा? बेस्ट केस कितना होगा? वर्स्ट केस कितना होगा? Okay, let's look at worst case. Who can tell me what's worst case? Let's look at worst case. What is worst case? Okay, in the worst case, what do we have to do? We have to in the worst case we will have to compare no, actually, right. So, worst case should be L plus m, right. We might have to do every possible comparison. Best case, what is the best case in your opinion? Huh? Okay, please. So, best case, it is not really clear what I am trying to say by best case, right, because what might happen is that if one of the sequences finishes, right, then I can just copy the next one. So, in the even the copying requires time, right. So, if you include the time for the copying, then it is always going to be L plus m, you cannot do anything more about it. But if you do not want to include the time for the copying, if you are just counting the number of comparisons that you do, then if you are just counting the number of comparisons, then you can do less, then it will be ठीक है. So this is what, okay, so you all understand this if you have. So in the worst case, why do you require L plus m comparisons? So you might require as many as L plus m comparisons, right. So in fact that was happening in this example, where till the very end not necessarily, right. So you know, if you count the number of comparisons that we did in this example, so for every element that we had to write out, we had to do a comparison, right, except for the last one. So you really required L plus m minus 1 comparisons, right, and that was the worst case, the number of comparisons if you are counting the number of comparisons. So you really require that many. right, and you can create sequences of arbitrarily values of L and M, so that you require L plus M minus 1 comparisons. Okay, good. So, we have understood merge, right, we have understood the merge step, we understood what merge sort is. So, let us try and analyze it, right, how much time, how many comparisons does merge sort take in all. So, if I had, so this is a quick recap of what we said so far. We have this sequence, we split it into 2, then we split this into 2, this into 2, and so on and on. When we had these single ones, then we merged these and we got 1 5, right. In the previous example I had shown you them going up, I have just kind of created a mirror image. So, I have merged them here, merged these to got 2 4, merged these to get 3 6, merged these to get 2 6. Then I decided to merge these, right, and I get 1 2 4 5. Here I merge these to get 2 3 6 6, and then I merge this to get 1 2 2 3 4 5 5 6 6. Yeah. So, you could also think of, pictorially, you could also think of this as what is happening, right, that you did your divisions. Of course, algorithmically it is the same thing, you are doing your recursive call, this is just a way of representing it. Yeah, why am I doing it this way? Because it will now be easy to compute what the running time is. Can you, by looking at this picture, say what the running time should be? No time spent in all of this part, right? Sorry, no time spent in the split part, but when we are doing the merges, we spend time, right. So, how much time do we spend in doing this merge? 2 units essentially, yeah, and how much in this? 2. Why am I counting 2? Length of the 2 sequences I am merging, I am always going to count that quantity, L plus M, right. So, ये 2 है, ये 2 है, ये 2 है, so each of these merges requires 2 unit of time. And how many such merges would I have to do at this level? N by 2 such merges. If these were n elements, then I would do n by 2 merges of 2 elements, right. So, total time would be n by 2 into 2 n. So, that is what is going to happen. We are going to see another way of doing this in a short while, doing this argument, but you should understand what is happening. So, each of these merges is taking 2 units and there are n by 2 such merges, and after that we get sequences of length 2. After this step we get basically sequences of length 2, as you can see. Now, we are merging these. So, each of these merges is now going to take 4 units of time, and there would be n by 4 such merges, yeah, and the next one would take, sorry, this should corresponds to this, and the next one would take 8 units of time, that corresponds to n by 8, and there are n by 8 such merges. N here is 8, so there is only one such merge, but in general there would be n by 8, and so you would get such a sequence. This is what you have to sum. This is the total time spent by your algorithm. Okay, we will see this in a slightly different way in a short while. So, we are going to analyze it once again using recurrence relations, right. So, we had used recurrence relations before. I am going to kind of say it once again, so that it is refreshed in your mind. So, typically for all recursive of algorithms of procedures which are recursive in nature, you can analyze their running time using recurrence relations, and it is basically an equation or inequality that describes a certain function in terms of its values at previous points at smaller inputs, right. So, for instance, so in particular for a divide and conquer kind of a problem, the time taken to solve t, if t of n denotes the time taken to solve a problem of size n, then it is equal to the time taken, look at this part, the time taken. So, suppose I divided it into some number of pieces, my n into some number of pieces. In our particular example, how many problems did we divide it into? 2, and each of the sub problems was half of the original thing, right. So, the sub problem, by sub problem size factor I mean by what factor have I reduced the size of the problem, yeah. So, that is the time required to solve each of the sub problems, this part. For each sub problem, that is the time required, that times the number of sub problems is the total time required to solve the various sub problems, plus the time required to do the division, plus the time required to do the combining. That would in general denote the be the recurrence that you would get. Yeah. And of course, this is when n is more. If n equals 1, then it is basically a trivial problem, and whatever is the time required to solve the trivial problem would be the value, would be kind of the base case for this recurrence, yeah, or the initial condition for this. So, for instance, for the merge sort problem, we divided the problem into 2 pieces, and each of the pieces was of size n by 2. So, the time required to solve a problem of size n by 2 to merge sort n by 2 elements will be t n by 2, if t of n denotes the time required to merge sort n elements. Yeah, we are using t of n to denote the time required or the number of comparisons required to merge sort n elements. So, then this is the kind of a recurrence we get. I have written theta n here, but you can just write n here, right, because that is the upper bound on the number of comparisons that we would do. Yeah, let us say that is the number of comparisons we are doing. So, this is the kind of a recurrence relation we would get. Is this clear to everyone? Right? And when we have a problem of size 1, if n equals 1, then this is just a constant, because we do not have to do anything really. Yeah. Okay. There are a bunch of ways of solving recurrences. We have only looked at what is called the repeated substitution method. What does that say? That basically says you expand the recurrence by substituting repeatedly and noticing any patterns that you get. Okay. There is another method which is called the substitution method, where you guess a solution to the recurrence, okay, and then you verify that your recurrence really satisfies that guess. In the course of this course, we will perhaps see examples of this way of solving recurrence relations. There is a third method called the master method, which basically says that, you know, if a recurrence is of this kind, then this is the solution for this recurrence, and you just plug in the values of a and b and you get your solution. Yeah. I personally do not like you to remember those formulas. It should always be possible to solve those recurrences, right, by just looking at them. So, but these are 3 ways, and then there is a fourth method, which is a recursion tree, that you draw out a tree of the calls that are being made, right, as we drew, and you count at each node how much time is being spent. Okay. So, we are going to look at, let us say, the repeated substitution method once again. So, suppose I am trying to merge sort n elements, and n is some power of 2, let us say 2 to the b, right. This will help us ease the analysis a little bit. So, recall the recurrence is t of n equals 1 and t of n equals 1 if n equals 1, and t of n equals 2 times t of n by 2 plus n if n is more than a 1. Yeah. So, we are just going to adopt repeated substitution. So, I just keep writing over and over again and see what I get. So, I get t of n equals 2 times t of n by 2 plus n. So, I have substituted once. Yeah. And now I am doing replacing this t of n by 2. So, this is the substitution step. I am replacing this t of n by 2 with 2 times t of n by 4 plus n by 2. Why n by 2? Because this is t of n by 2. Yeah. So, this part ka half is coming in here, and this part whatever is n by written here, it comes again here, plus n, and now I just expand this, which means I write it as 2 square t n by 4 plus 2 n. Once again I substitute for t of n by 4 and I expand to get this, and now I have to observe a pattern basically, right. What is it that is happening? I get 2 square times t of 4 times t of n by 4 plus 2 n, then 8 times t of n by 8 plus 3 n, and so on. So, in general at any step I am going to get something like, after I have done this thing I times, I get 2 to the I times t of n by 2 to the I plus I times n, right. That is what the 3, the 2 and the 1 here mean. And now if I choose I to be log n, what do I get? I get 2 to the log n times t of n by n plus n times log n. Now, t of n by n is 1, 2 to the log n is n, t of 1 is 1. So, this becomes n in all and this becomes n log n. So, I get a total of n plus n log n, which is order n log n. Yeah. So, that is the total time taken by this procedure. Everyone understands this? So, simple, very simple recurrence, you can just solve this using repeated substitution. Yeah. Okay. Now, if you are understanding this, let me ask you a question. Does this give us the average case time? It's in all cases it will be the same time, right, because we have written that the time to combine is n, right, this is the combining time. Now, if the time to combine is always n, so to say, right, because we need to look at our merge step more carefully. When we look at our merge step more carefully and I will actually show you the code, you will see that you really need that much time, you can't do in less than that time, as many elements as you are trying to merge, total number of elements you are trying to merge, right. So, you really need that time. So, what you have actually argued is that t of n, the time for merge, the time for merge is theta of n log n, right. So, it is not big O, it is not omega, it is actually theta, it is always you take this kind of a time. Yeah, it is bounded by some constant times n log n, upper bounded and lower bounded also by some constant times. Right. Now, suppose I had, instead of this 1 here, I had a C. What do you think would be the solution for this? But Cn plus n log n? Why am I doing this? Okay. So, ये ऐसे हो जाएगा, नहीं, sorry, yeah, that's right, n into C plus n log n, great, good, n into, so this is by just looking at the solution, right, you can see that this is what you would get, अगर ये पहला वाला C था तो, नहीं समझ में आया? हाँ, ऑर्डर आपका n log n होगा, provided C was not that big, right? If C was n squared, then it. Right. So, the one way of also thinking of this entire thing is what we said, a recursion tree. Let's draw out a recursion tree for this, right? So, क्या किया हमने n साइज का प्रॉब्लम लिया, मुझे वहाँ नहीं लिखना चाहिए था n, ओके, हमने एक n साइज का प्रॉब्लम लिया, उसको डिवाइड किया इंटू 2 n/2 साइज प्रॉब्लम्स, राइट, and then उसको divide किया into 2 n/4 size problems and so on and on. Let me write down the total time taken in the division and the combining at this node itself. इसको divide करने में और इन दोनों को combine करने में जो मुझे time लगा, कितना लिखना चाहिए फिर मुझे यहाँ पर? Divide करने में कोई time नहीं लगता और इनको combine करने में n time लगता है, तो I should write down n here, right? यहाँ पे I should write down n/2, right, and so on and on. Yeah? तो अगर ये यहाँ पे मेरा C होता तो कहाँ पे C लिखूंगा मैं? लीव लेवल पर, यहीं पे C आएगा और कहीं नहीं आएगा. Yeah? And now what's the total time taken? It's basically the sum of the numbers written in these nodes, which is n here. This level पे total n होगा, next level पे भी total n होगा, and so on. एक्सेप्ट लास्ट लेवल पे जहां पे टोटल सम Cn होगा। तो Cn प्लस ये log n लेवल्स हो गए, तो Cn प्लस n log n हो गया। ठीक है, अगर मैं यहां पे C टाइम्स n लिखता, यहां पे भी C टाइम्स n होता, तो बेसिकली सब कुछ C से स्केल हो रहा है, राइट। हर जगह यहां पे हमारा C लिखा हुआ होता, तो ये सब Cn हो जाते और ये हो जाता C ऑफ n प्लस n log n। ठीक है, that's okay, right? I have not said that these C's are necessarily constants, right? There could also be something which depends upon n, in which case, yeah. Okay, so this is how, this is another way you can view this thing, right? You can draw out this tree and you can write the total time being done at that node in the combine and the divide step. Great. So, so this is what